number, so Hess's law. Okay, Hess's law. Hess's law. I'm going from a particular set of reactants to a particular set of products the change in enthalpy is the same. By the way, when I say change in enthalpy, what are you supposed to be thinking?
Change in internal energy.
Close. Heat. It's about heat flow. The change in enthalpy is the same regardless of the number of steps. And steps involved. Okay, so basically what we're saying is this. Really then it means that the enthalpy of the reactants, the amount of heat that the reactants contain, and the enthalpy of the products, the amount that the products contain, are the same regardless of how they got there. So it means they're both state functions. So if you have a chemical sitting in front of you, it has a certain amount of enthalpy associated with it. If you have a product sitting in front of you, it has a certain amount of enthalpy associated with it. It doesn't matter how you got there. So for instance, think about it like this. If you have a pile of sugar sitting in front of you, it has a certain amount of delta H associated to it. If I had more sugar, I'd have more delta H. If I had less sugar, I'd have less delta H. If it wasn't sugar, it'd be a different delta H. Be a different amount of heat. So basically we can say, so here's where you should probably pick up your notes again. Basically, enthalpy of reactants / products are state functions. Little tips here for what we're going to do going forward. Let's say we have a sign for delta H. That sign tells me what? If it's what or what?
Positive or negative.
Okay. Endothermic or exothermic. Is everybody good with that? What's endo? Yeah, so what sign? Oh, positive, and then therefore exothermic is negative. Okay. What do you suppose happens if I reverse a reaction?
The signs will flip.
The signs change. Does that make sense? So if something releases heat going from reactants to products, if I go from products back to reactants, it's going to absorb heat. It's going to be a reverse process. So the first tip is, if a reaction is reversed, if a reaction is reversed, then the sign for delta H changes. Okay, so that's one trick. And the second trick is that, like, what do you think happens? Like, let's say you start out and you got a delta H. It's whatever it is. It's positive, it's negative, it's a number, whatever it is. And the thing you're concerned with has the coefficient 1, okay, as the equation's written. What do you think happens to delta H if I rewrite that equation with the coefficient being 2, basically inflating all the coefficients, doubling them? What do you think happens to delta H? It also doubles. Because remember, delta H for an equation like you're going to have tomorrow is written as the equation is written. So if you have a delta H at an end of an equation, it says 100 kilojoules. All right, that's per however many moles as indicated by the coefficients. The coefficient's 1, and it's 100 kilojoules. Okay, or 100 joules, whatever I said. But if I inflate that to 2, then I have to double the amount of kilojoules as well. Okay, so we'll see that in action here in a second. The second tip is if the bless you, if the coefficients in a chemical equation are multiplied, then delta H is multiplied by the same amount. Is multiplied by the same amount. Okay, so we'll do an example. Example will take a few seconds. Example, calculate delta H for the following reaction. 5 carbon solid plus 6 H2 gas yields C5 H12 liquid. Okay, so now the way we're going to start out doing these problems, and then it's going to get even simpler, is this. I'm going to tell you an equation that I want you to calculate delta H for. And then I'm going to give you a series of a bunch of other equations, which you can think of as the steps to get from the reactants to the products. And they're basically puzzles. And you got to figure out how to rearrange these equations so you can get rid of everything that you don't want, but include everything that you do want. Keep in mind they have to work out. You know what I mean? So like I can't throw you, I'm not going to throw you curveballs here, right? The other thing I want you to keep in mind with these particular problems is I do not have an infinity of these. If you don't do your homework and you wait to the last minute, you say, can I have more problems? I may have given you all the problems that I have. Because I can't just make these up off the top of my head. They have to, they're very complicated to put together, is my point. All right, so now, let's say, I want to do that, but let's say this is the information I'm given. Given, let's say C5H12 liquid plus O2 or 8O2 yields, and that's gas, yields 5CO2 gas plus 6H2O gas. And there's a delta H for that equation equal to negative 3244.8 kilojoules. So again, just like in your test that you're going to take tomorrow, that means it's negative 3244.8 kilojoules per 1 mole of this, per 8 moles of this, per 5 moles of this, per 6 moles of this. Yep, absolutely. Okay, I'm going to give you a couple more equations here. Here's another equation. I'm going to give you this one. It's carbon solid plus O2 gas.
This is all for one problem?
This is all going to be for one problem. So you're going to see these are pretty, they look long and intimidating, but they're not that bad. CO2 gas. So I'm just giving you some background information right now. Basically, I'm saying, let's say these are reactions that we already performed in the laboratory and we know the results for them. So delta H for this one is equal to negative 393.5 kilojoules. And that's per 1 mole of each of those things because everything's in terms of 1 mole. Now I'm going to give you one more. I could give you 2, 3, 5. I could give you a whole bunch of equations, but I'm going to give you 3 for this example. Let's say we have 2H2 gas plus O2 gas yields 2H2O gas. And this has a delta H equal to negative 483.5 kilojoules. Okay, so I've just given you a bunch of information. The first thing that I would do is I would number my equations so I can tell them apart. You can letter them, you can call them A, B, C. I like to call them 1, 2, 3. So I'm going to call that equation 1, that equation 2, that equation 3. So what my job is to do is to rearrange these equations so I can model the initial equation. Now the way that I approach it, there are multiple ways to do this, so you can read the book and see what they say, which is basically the same thing as I do. Or you can trial and error it other ways. But what I do is I go to my original equation. Okay. My original equation is right here. That's the one that I'm trying to emulate. And what I'm going to do is focus on one thing at a time. And the first thing I'm going to focus on is this 5C. Notice that there's a state there too. I got to pay attention to states as well. So you can't treat a liquid like a gas or a gas like a liquid. They got to match. So when I look here, I say I need 5 carbons here. Then I go down and look at these equations I got to choose from. And fortunately, there's carbon here, and it's only in one equation. Now, if carbon was in this equation and this equation, then there wouldn't be a clear-cut choice of which one to do. So you want to focus so you don't have choices.
So if it's like carbon and polyethyl ions, you can't use it?
Correct. It's got to be exactly like it was, yeah. So does everybody see that up here, we have carbon, solid, on the reactant side, and there's 5 of them. Here I have carbon on the reactant side, but there's only 1 of them. So what am I going to do with this equation? Multiply it by 5, okay? So down here, I'm going to come down and I'm going to say, I'm going to take, first thing I'm going to do is I'm going to take equation number 2, and I'm going to multiply it times 5. Very good with that? And what that gives me now is I'm going to multiply all the coefficients by 5. So I'm going to get 5C solid plus 5O2 gas yields 5CO2 gas. Now
So would delta H be multiplied by 5 also?
delta H will be multiplied by 5, yep. So the whole reason I did that was to get this fixed into the equation. And I like to do is I like to go circle these things. I like to go say, all right. So I brought that first equation in to match that 5C. That's the only thing I got matched right now. Now I can look around and see if anything else happened, because sometimes good things happen. There's 6H2 there. Well, I don't have any H2. There's C5H12 on the product side. I don't have any C5H12. So this is stuff that's going to have to go. We're going to have to get rid of that stuff. But what I do is focus first on bringing in what I need to bring in. Because a lot of times when you bring in what you need to bring in, the things that you want to get rid of go away. Okay? So the next thing I'm going to focus on is probably this 6H2. And I go down to my equations, and do I have any equations that have H2 in it?
Number 3.
Number 3, but what would I have to multiply it by?
3.
3, right? So this time I'm going to take equation number 3 and multiply it by 3. So I'm going to take number 3 and multiply it by 3. So that's going to make us 6H2 gas plus 3O2 gas yields 6H2O gas. And the whole reason I did that was to bring in this 6H2 gas to match this 6H2 gas. Yep.
So do they have to be on matching sides then?
Yes. Yes. Okay, so again, I'm going to continue just focusing on things that I needed to focus on. So the next thing I want to focus on is my last product now, C5H12. Now, do we have any equations with C5H12? The first one, but what's the problem? It's on the wrong side. So guess what you have to multiply it by? -1. We don't want to change the coefficients, but we want to reverse the sign for delta H, because we're going to go in reverse. So I'm going to take number 1 times -1. Number 1 times -1. So it means everything that was on the product side is going to be a reactant now. So I've got 5CO2, 6H2O. 5CO2 gas plus 6H2O gas yields C5H12 plus, that's liquid, plus 8 8O2. O2 gas. So I basically just took equation number 1 and wrote it in reverse. 5 and 6 CO2 and H2O, 5 and 6 CO2 and H2O, C5H12 and 8O2, C5H12 and 8O2. And the whole reason we did that step was to bring that into play, which matches this. Yes, John?
So when you use like, if it said C5H12 liquid had like a 3 in front of it, would you just multiply by -3?
No, you multiply it probably by a -1/3. Because I only want 1. If there was a 3 in front, I would want to decrease it. That makes sense? And you will see as we get into more complicated ones, you're going to start dealing with having to multiply by a fraction too. Okay. All right, now let's see what else happened here. Does everybody see, though, that this 5CO2 and this 5CO2 cancel? It's like they're spectators. They were there at the beginning, they were there at the end, they didn't do anything. They didn't change. And I've got 6H2O and 6H2O. Those cancel because they're on opposite sides. If they're on the same side, they add. We went through this when we were doing other types of equations in the past. And then this 8O2 cancels with that 8O2. Anybody with me there?
Will it always cancel out?
They have to work out, yeah. And that's why I'm saying I can't just make these up, because they got to work out that way. Right? So now all we do is take just all that we just did and summarize it. So delta H is going to be equal to number 2 times 5 plus number 3 times 3 plus number 1 times -1. So I just took what I just said, like the stuff I kept on the side there. I'm just going to do that. And so delta H equals, well, number 2, I got to go up to its delta H value. That was -393.5. -393.5 kilojoules times 5 plus number 3 was -483.5. -483.5 kilojoules times 3 plus number 1, which was a bigger number. Number 1 was -3244.8. -3244.8 kilojoules times -1. And now I'm just going to sum all these things up. So this comes out to be, hey, thanks, sir. Appreciate it. He is not here. He is not here. Thank you. Chris Malik never made it, right? No, I knew it, but I just figured I'd say something stupid. Okay, so let's see. So what do we got here? We got negative. Let's just do this like this. Let's see. I'm going to have, I'm doing my 393.5, negative 1967.5, negative 1967.5 kilojoules, plus negative 1450.5 kilojoules, plus 3244.8 kilojoules. Or delta H equals -173.2 kilojoules. Okay. I don't know about you, but I think they're fun little puzzles, personally. I think they are kind of neat. I get like a little sense of satisfaction when everything works out real nice. I don't know why, I still do to this day. But I kind of like this stuff. So basically, this is the way it works. I give you an equation, which you are trying to emulate, right there, with all the circle things. Then I give you a series of equations and their associated delta H values. And you focus on bringing in each reactant and each product that you need, and not worry about canceling until the end. You may find out in the end that some things don't cancel away, so you may need to use an equation just for the sake of canceling.
Is there gonna be equations where like you have like 2 C's, like
Yeah, it could be.
so like in my situation, is it just like pick
And if you only wanted one, are you saying, or if you had, like, if it said, like, let's say it said 2C here and you wanted 5,
Yeah.
right? I would multiply this equation by 5 halves.
No, like if there was a C in number 2 and number 1.
And what?
If there was like a C in number 2 and number 1, is that gonna happen?
Yeah. So let's say you have C in number 2 and number 1. What I would do is skip C and go to the next thing. Because what's going to happen is sooner or later you're going to pull one of these equations not for C but for something else, and then you'll know that you can use the other equation for C. So basically put it this way. If you have multiple choices of which equation to use, skip it. Go to something else. Yeah. You want no choices, you know? That'd be the best. You good there? Yep.
Do they have to be the same state?
Yes, they do. They have to be the same state. Because, like, for instance, CO2, I think it's enthalpy of formation, which we'll talk about them later. From gas to liquid is like 40 kilojoules different or something like that. So it does matter, the states. So you bring your stuff in, keep track of what you're doing right here. Keep track of what you're doing right there. So when you get done, oh, I don't know what happened there. I think I erased it. There it goes. So, and again, this should have been, I erased some stuff by accident. That should have canceled. Okay.
You erased the O a little bit too.
Which where?
Right in the original. H2.
Okay. Was that H2O or H2?
It was H2, yeah.
H2 gas?
Yeah.
Thank you. Good. So that's good?
Mm.
Good. Right. Yeah, sometimes I erase and I don't want to do that. Okay. And so keep track of what you're doing here. What I'm multiplying each equation by. Remember, you're going to multiply it by a number that gives the right coefficient. And then the sign, it's positive if you're going to leave it with reactants on reactant side, products on product side. If you're going to flip it around, negative. Then I like to write down what I got, what I said, and then I sum everything up. Yep. Yep. So we all good there? Okay.